welcome everyone back our class. So today I will introduce about the Gram-Schmidt orthogonal process. Orthogonal, that's kind of how to transform the angle. So that is the basis for how we represent the quantum state and the transform. So today is one lesson for the introduction to the quantum computing and programming. So we will look what is the Gram-Schmidt. Okay, this is a kind of when we represent the quantum state, we check about we have vector v. But how this kind of the vector or this kind of state will be changed? Yeah, will be changed or change state from this one to the other. So for example, we have a given two vector. We have a vector u and we have a vector v. So we projection, that means we can reflect a two vector from this one to this one and see how the relationship between the two states. So that's called the projection on the vector. So you see, after we project into the vector, we can say the value, projection vector v is equal to this one, and replace the remaining one if the the vector v, the minus projection. So we can see this one. So this one we can hear a kind of square, or this one is kind of perpendicular. Yes, perpendicular. Yeah. And in the high school, you already learned about this part, how to calculate the length of this one. Okay, so today we look more details. So remember the last lesson we already learned about the inner products, right? This is symbol to define. Yeah, we have an inner products. So v u. So if the projection from the vector u and to the vector v, so equal to this is inner products. Inner products. This traditional, okay, traditional inner products, vector u and vector v, and this one traditional inner products for vector u itself and multiply with the u. Yeah, this is kind of inner products. Okay, inner products. Inner products. Yeah, remember about the last lesson. Yeah, and we see the similar the symbol. And here is a kind of when we have a two vector, we have projection vector, and we have the reverse way. We have the remaining part. So this is tie up to the two part when we have a relationship is called perpendicular. Perpendicular. This is perpendicular. Okay, this angle. Actually, that's kind of about 90 degrees. Okay, so and here is how we can calculate and remember. Is this one is when we have inner products and we minor the inner products with the projection. So this is kind of calculate, and the final one we see about the inner products for u and v, minor inner products u and v, of course is 0, right? So that is one reminds if we minus the vector u over the projection over this part. Yeah, projection. That means project again. So they will be have the same value. Yeah, project again. After we have projection, yes, we have projection from vector u over vector v. So we have this kind of formula, right? And we can transform. Remember, after we have inner products, standard inner products, we can transform inner products. V u's, you can transform to the u star v, right? Or this one, I think the u and v are similar, u star v. Yeah. So this is how you transform between the two. And this one is conjugate, right? Conjugate. Yes, this one is equal to, I remember, is equal to the or u1, yeah, v, yeah, u2, v, yeah. Okay, so this is how we can calculate. Yeah, and remember about the inner products in the last lesson. Yeah, and here is we can calculate a value in example. Actually, over here we have two vectors. For example, we have two vectors. This value in the u and v. So how we can find the projection from the vector u and to vector v, or in reverse way from the vector v to vector u. Okay, from the first projection from vector u to vector v, so you can find is equal. I think is equal to the standard inner products, or you can calculate by the u and v, something in u stay. You can check previous one, this one u multi u, and this one standard products, standard product. So you can calculate this one by separate. Each calculate one, you can this, and calculate the total. And when we have a vector, the total vector, so each vector over here have one the number, and we can multiply with this one, and we can have this kind of value. This kind of value after we multiply. This kind of vector is 3. We have a multi. Actually, this one we have we will have this guy. To have this one, so we have this guy. So I think this one is when we have equal to the 3 number. This guy, I think it's 1. So after you multiply, is equal to this part. Okay, Similar, this one is after we projection. Remember, if we projection from the u and to v to u, so you can see this one is different. Okay, different order. We want u and v first, u and v, and the dominator will be changed. This dominator, this one from u and v, so dominator is u. Okay. If from the v to the u, so we will the v in the dominator. Okay, now we have projection to the one vector. So what is the Gram-Schmidt orthogonal process? Okay, we have two vectors. So example, we have a vector v, and we have basis. This guy basis. Okay, a basis vector. So if the process can make a kind of basis to become, if we have a vector b is not kind of orthogonal. So if the process can transform between the non-orthogonal, this is non-orthogonal to the orthogonal, so it's called the Gram-Schmidt. If you can see, we can transfer between the vector b and we can this kind of projection, right? This kind of projection. So remember from the last slide, we have this part. We have this part, right? We have this part, and we can minus from the vector one element vector, and to remain the projection from each element. So we can transform from the one non-orthogonal, the set can to the orthogonal, the set. So now we have this guy. We have a vector d is orthogonal, the basis for vector v. So this one it can can follow this one. Okay. And if you see over here, we have this guy similar my previous one. Previous one. So actually, we as emphasize that is we have a result about the vector u a1 to un. That's after we transform. So we can make process. Okay, how to prove the Gram-Schmidt? So this is how to prove you can transform between the non-orthogonal to the orthogonal the part. So for example, this one is standard inner products, right? The standard inner products. So after you transform, use conjugate. Yeah, you can conjugate and you multiply this one, and actually after you this one and this one to this one, right? You can split to this part, and so and after you multiply and projection, you can see this kind of two value can equal to the 0. So that means it relationship between the two the non-orthogonal is have a relationship in each other, but we need to find a way to to convert. And Gram-Schmidt orthogonal process that helps us to convert and to transform between the model. And here is kind of how to go proof. So this one is you can check more in the slide. So the key point, here we can transform between the orthogonal, the set. After we derive, so the values will be equal to greater or equal to 0. And equal to 0. And the other thing, we have a linear independence. Independence. So if we have a linear independence, that is equal to 0. So we can have the x value in this kind of a linear function need to have equal to 0 too. You can see R, R, R1, R2, or Rn. If we want to make sure this one is 0, so x of this kind of element need to equal to 0. Because 0 multiply any value we equal to 0, right? Okay, so the Gram-Schmidt orthogonal, the process, this one to make sure the x element in this vector after we transform, we need to have a linear independent set with and element. Okay, so this kind of the basis the vector v. Okay, the one after we can transform to orthogonal, non-orthogonal to the orthogonal. So how we can represent in the quantum inner products? So previous we only care about the standard inner products, right? So over here we can represent again. If we project from a vector v u into vector v, you can transform to the this is quantum, right? Quantum inner products, quantum inner products. And if you see over here, it's similar. Is equal to previous is equal to v u, right? This one is u, right? This previous one is standard, and this is quantum inner products. So but over here, if you want to transform and you want to calculate the value between these two value in quantum, the inner products, it cannot preserve orthogonality. So that is kind of one of character in the quantum space So okay, so now if you use the quantum, the part, you can check if this one have a perpendicular or not. So this is kind of formula. And after you calculate, see this value is not 0. So we can say this is not. This is not perpendicular. So that means, perpendicular in the quantum space may be more difficult than in the traditional model. Because, in the space, something like this we have in space. So if we do not use 2 dimensions, so it's very hard to make a reference to plate to have, perpendicular like this we have. If this one is equal to 0, yes, that's sure. That can be a kind of perpendicular, perpendicular, the value. Okay, so over here, this lesson we take care about the Gram-Schmidt, right? Yes, Gram-Schmidt. And we transform between the orthogonal, non-orthogonal to the orthogonal the space. Yeah. So I hope everyone can match this one and think more how to to transform between the two one. This part a little bit difficult, but I think you can got it. Thank you everyone.